We're looking at section 5.2, which is the polynomial division and the division algorithm. For our topics for this section, we'll be looking at the division algorithm and the remainder theorem, how to do polynomial long division, how to do synthetic division, and constructing polynomials that have certain zeros that are given to you. Alright, the division algorithm basically says when you divide a polynomial, you divide it by a certain divisor so that the quotient times the divisor plus any remainder that you have gives you back your original polynomial. And that's what we get when we learned division many years ago in elementary school. The degree of the remainder has to be less than the degree of the divisor, or the remainder can be 0, in which case we say that the divisor divides evenly into the polynomial. If it does that, then it's a factor of the polynomial. So later, when we were trying to find zeros, we're using this skill to find zeros, we look for those remainders of 0 because we know that that's a factor. Zeros and linear factors. The number k is a 0 of a polynomial if and only if x minus k is a factor. And so in this case, you could have your quotient times your divisor, which is x minus k, and get back your original polynomial. And that's basically what they said on the slide before this. But if it's a factor, if it's a 0, then k is an x-intercept in terms of the graph of the polynomial. So the remainder theorem says that if the polynomial is divided by x minus k, the remainder is p of k. So p of x equals q of x times x minus k. So in other words, if I put the number into my original polynomial, then I could find out what the remainder would be. So we're going to divide this polynomial using long division. I want to go through just a little bit a reminder of what we did when we did division a long time ago when you first learned long division. And so say we have 546 and we want to divide that by 3. Now we'll divide that by 6. I hope it won't divide evenly, but it might. Okay, I'm going to change that because I think we'll do I'm going to divide 746 divided by 5. Okay, so we first look and say how many times will 5 go into 7. It will go 1 time. 1 times 5 is 5. Subtract it, or change the sign. Then we add them together. So 7 plus negative 5 is 2. Bring down the next number, which is 4. Then we try to see how many times 5 will go into 24. Well, it will go 4 times. 5 times 4 is 20. Change the sign. 24 plus negative 20 is 4. Bring down that next number, which is a 6. 5 will go into 46 9 times. 9 times 5 is 45, and we have a remainder of 1. And 1 is less than 5. It has to be, or we would have done something wrong. So we could write our answer is 149 plus 1/5, our remainder over our divisor. Sometimes we used to write 149 with a remainder of 1, but most of the time we're going to write our answers in this format for this particular situation. So that's just kind of a reminder of long division, because a lot of the polynomial division is exactly the same as long division as far as that process of bringing down the next thing and adding a negative, if you change the sign and add, it's the same as subtracting. And so we're going to look at dividing our polynomial. You want to have all powers of x represented, starting going from highest to lowest. So we've got x squared, x, and then a constant. So we've got x squared plus 2x minus 24. And we're going to divide that by x plus 6. And x, we just really look at the first numbers or variables in this case to see what we want to put up in our quotient. Well, x times x will give me x squared, so I'm going to put an x there. I'm going to get rid of those lines just because I don't need them. Now but when we multiply back, we multiply by both things. So x times x is x squared, so I put that right under the x squared. X times 6 is 6x. I put that under the 6x, and it's positive. Now I'm going to change the signs all the way across in that second line, and then I'm going to add. This first term should always add to be 0. 2x plus negative 6 is negative 4x. And I'm going to bring down my negative 24, the next thing that's there. Now, what times x? It will give me negative 4, so it's negative 4. Negative 4 times x is negative 4x. And negative 4 times positive 6 is negative 24. Change the signs all the way across. And in this case, both of them are going to add out, and our remainder is 0. So that means that x plus 6 is a factor of this original polynomial. And so our answer, for our division, our answer would be x minus 4. Okay? And so they're going to show you the same thing. They distribute that negative. I just change the signs all the way across and get the negative 4x. Bring down the negative 24 and come up with the same answer that I did, a remainder of 0. And so the quotient x minus 4 is the answer with a remainder of 0. Okay, this is the process for long division. Arrange the terms in descending powers of x. Divide the first term in the dividend by the first term in the divisor and put that in the quotient. Multiply the entire divisor. Write that beneath. Line up like terms, subtract the product, bring down the rest of the original dividend, repeat the process until you're done. So here we've got a big polynomial, and you're dividing by 2x squared minus x plus 3, so you've got a larger divisor as well. The problem here is, one problem you see is there's a missing power of x. We've got x to the 5th. We've got x to the 4th, x cubed, x squared. We're missing an x. And so how do we write that? The other thing is your divisor is a second degree divisor. When we do synthetic division later on, you won't be able to do synthetic division with this kind of divisor. It has to be linear, just an x minus a number or x plus a number. But we can do this with long division fine. It's no problem. So we're going to start with writing down our dividend and our divisor. Again, we're putting that 0x in for our missing power, or for our missing x. Then we say, okay, 3 times 2 will give me 6. So in the quotient, I'm going to need 3x cubed, because that's what we'll multiply by 2x squared to give me 6x to the 5th. But then I have to multiply by everything, so I'll have 3x cubed. I'll have 6x to the 5th minus 3x to the 4th plus 9x cubed. Then I would subtract that, in essence, then change the signs all the way across. And so that's going to become a plus 3x to the 4th, so I'll have minus 2x to the 4th and plus x squared, and then bring down the rest of the divisor. You can just bring down the 15x squared if you want to, and that's fine. Now, what times 2x squared is going to give me 2x to the 4th? Well, that would just be a negative x squared. Then multiply by everything in the divisor. Negative 2x to the 4th plus x cubed and minus 3x squared. Change signs all the way across. In this case, what's going to happen is your first two terms are going to add to be 0, and you're going to be left with negative 12x squared. Bring down your 0x and your negative 19. And to get negative 12x squared, we're going to have our last term in our quotient be negative 6. Okay, so negative 6 times 2x squared is negative 12x squared. And then we have plus 6x and minus 18. Change signs all the way across. So it would be plus 12, minus 6, and plus 18. We're just left with negative 6x minus 1. And you can see that x is less, the remainder degree is 1, the divisor degree is 2. So the remainder degree should be less than the divisor degree. And when you write your answer then, you're going to write it as 3x cubed minus x squared minus 6 plus the fraction, which is made from the remainder over the divisor. Okay. Be careful, this is just a caution, one of those caution slides. Be careful on that when you have your negative, and you be sure you change your signs all the way across before you add. After you when you subtract, basically, are going to subtract that second line. Be sure that you do that, change the signs all the way across that second line. If not, you'll miss something and you'll make a mistake. Alright, so here we're dividing by a complex number. And that can be a little bit of a problem, but let's look at what we've done here. First, we're going to list all our missing powers of x. So we have 0x cubed, 0x squared, 0x, and then our 1. And in the divisor, too, there's a missing power of x. We have x squared plus 0x plus I. Okay, so we're going to start within our quotient. It'll be an x squared. So we have x to the 4th plus 0x cubed plus ix squared. And then that's going to be a negative all the way across when I change the signs. And so I'll end up with a negative ix squared and bring down the 0x and the 1. Okay, so going to the next slide. We will have to multiply by a negative I in the numerator in order to make that match. So we have negative I squared, and we have 0x. And we get the 1 by negative I times I is negative I squared. And negative I squared, remember, is negative 1. So is 1. So what we've got here, we have a negative, and then the I squared is negative 1. And that's how we get a positive 1. And then the signs here, when I distribute this negative, this becomes a positive, this becomes a negative, and this becomes a negative. Okay, I've distributed that negative all the way across. And so this cancels, and that cancels, and our remainder is 0. So we have x squared minus 1 is a factor of our original polynomial. Okay. And so it turns out that that can be x squared minus 1 and x squared plus 1. Okay, for synthetic division, it's actually easier, but there is again the caveat that it can only be a linear factor that you can divide by. So if your divisor is x minus k, remember the k you're going to divide by is not negative, it's just that number. It's just the k. If it's a negative number, the factor will be x plus k, because that means we've got x minus a negative k. So to have a negative number, if I divide by a negative number, in the factor it will be a positive factor. Now this is confusing I think, to read through these steps. So let's just go through and do a couple examples, because synthetic division, really, most people like it. It's a little easier than long division. You don't have to worry about changing the signs and that sort of thing, except for your original divisor. So looking at example A, we've got a polynomial, the highest degree of 4, that's the highest power of x. Our k is 5, that's what we're going to divide by. All the powers of x are there. We've got 4, 3, 2, 1, and then the constant. In B, though, we're missing several powers of x. We've got 8, 7, we're missing 6, 5, and 4, and we're going to have 3, 2, 1, and then a constant. So we're going to have to put several zeros in there for placeholders when we get to B, because placeholders have to be there for synthetic division. Let's start with the simpler one, which is a. So there's our original coefficients. We don't list the x's, we just list the coefficients, and we're dividing by 5. And the way you do this is I bring down my first number, just bring it straight down and write it here, -2. Then I multiply 5, which is my divisor, by -2 and get -10. Rewrite, once you multiply, you go to the next one over and write your answer. Now I'm going to add the 11 and -10 and get 1. Then 1 times 5, 1 times the divisor, is +5. Add those two numbers and get a 0. 0 times 5 is 0. -3 plus 0 is -3. And -3 times 5 is -15. And 15 and -15 is 0. So 5 is a factor of that original polynomial. Now, if I want to write the polynomial, if I want to write the answer, one thing you have to remember, when we started, we had x to the 4th, we had x cubed, we have x squared, we had x, and we had our constant. When I have my answer, I've divided by, this really is a factor. This represents a factor of x minus 5. So I divided that original polynomial by x minus 5. So that means there's one less x in the answer. This is x cubed, x squared, x, a constant, and then this will be my remainder. So my answer is -2x cubed plus x squared. There is no x, so it's just -3, and there's no remainder. So that is the quotient. And I could, if I multiplied this by my x minus 5, I would get back to my original answer. Okay. So they're going to show you that they did the same thing. Okay. We get a 0. 0 times 5 is 0. Add, multiply, add again. Okay, and then the depressed equation would be the -2x cubed plus x squared minus 3, which we just talked about. All right, let's go on to our next example. Again, this have to have all those placeholders. We had power of 8, 7, 6, 5, 4 were zeros. You're going to divide by -3. So bring down your 3. 3 times -3 is -9. Add and get 0. -3 times 0 is 0. Add and get 0. Multiply and get 0. Add and get 0. Lots of zeros. Okay, now I'm going to finally get a -1 when I add. -3 times -1 is +3. But I get a 0 again. -3 times 0 is 0. Add and get 1. -3 times 1 is -3, so I have -4 as a remainder. So I started with x to the 8th. So remember then, 1 power less, this is x to the 7th. 6/5, 6, 5, 4, 3. This is x squared. This is x. This is my constant. And this is my remainder. Okay. And the factor that I divided by, because that's a -3, this factor that I divided by would be represented by x plus 3. So if I wanted to write this as an answer, the quotient would be 3x to the 7th minus x squared plus 1 plus -4 over x plus 3, or you could say minus 4 over x plus 3, either way, since that's a -4. Okay? And if I put -3, the remainder theorem, when we talk about the remainder theorem, tells me if I put -3 into my original equation, I should have gotten -4. That would tell me that -4 is a remainder. And so the way you would do that, if you wanted to see an example of that, is we'd have to go back. Our original equation, I can get it from up here, was 3x to the 8th plus 9x to the 7th. 654 minus 3x cubed minus 3x squared plus x minus 1. So what they're saying by that last statement on this slide is if I said 3 times negative 3 to the 8th power plus 9 times negative 3 to the 7th power minus 3 times negative 3 to the 3rd power minus 3 times negative 3 squared minus 3 minus 1, then I would get, my answer would be negative 4. And I'm not going to multiply that out, but it does work. Okay. Now we've got a synthetic division using a complex number, which is very difficult. And I want to talk about complex numbers for a minute. Complex numbers are, when you have a complex number as a factor potentially, it always comes in pairs with its conjugate. And if you remember, we would think, based on what we saw before, that this is what we would use to divide by. But it's not going to be what we use to divide by. And so I'm going to put that up on the slide, and then I want to talk about it in a minute. So let's go back and show that when they list it for our setup for our synthetic division, you notice it's not minus 1 plus I, or it's not 1 plus I, it's 1 minus I. Well, why is that? The reason is that we have conjugates. We have 1. What we're going to divide by is either going to be, I need to go back to the next. What we're going to divide by is either going to be 1 plus I or 1 minus I. Those are the complex conjugates that could be zeros. Well, remember our factor, when we have x minus k, I have x minus 1 plus I, or it might be x minus 1 minus I. Well, which one is it? Well, we have to distribute that negative to see which one matches the denominator that we have. So this would distribute as x minus 1 plus I, and this would distribute as x minus 1 minus I. So the one that matches our denominator is this one. So that is the x that we divide by. Okay, the 1 minus I. And so that's confusing, and I'll grant you that it's confusing. So be aware, if you're dividing by a complex denominator, you're going to have to give it some thought. The numerator is not so bad. The negative 3 is in front of the x cubed. 5 minus 2i is in front of the x squared. Negative 4 plus I is in front of the x. And 1 minus I is your constant. Synthetic division is the same, but with complex numbers there's a few little complications, and if you're not careful, the divisor is one of them, but there's also another thing we're going to get to as we go through here that can throw you off if you're not careful. So the first thing we're going to do is multiply the negative 3 times the 1 minus I. Put it up here. So we're going to get negative 3 and then plus 3i. That was pretty straightforward. 5 minus 3 is 2, and positive 3i minus 2i is minus I. This next multiplication is not as straightforward, because we've got to multiply the divisor, which is 1 minus I, times 2 minus I. And we're going to have to divide or FOIL those binomials, or take this 1 and distribute it across there. So 1 times 2 is 2. 1 times negative I is minus I. Okay. Then we have negative I times 2 is minus 2i. And then negative I times negative I is plus I squared. But remember, every I squared is replaced with a negative 1. Okay? And I made a mistake, I can see right now, so I need to go back. So let me erase this. Okay, so when we add these two together, we're going to get 5 minus 3 is 2. Get my pencil. And then plus 3i minus 2i is going to be plus I. So now we have to go and we have to multiply our divisor, 1 minus I, times our 2 plus I. Okay? So when we distribute the 1 across that second set of parentheses, we have 2. And then we have plus I. Then we have minus 2I. And minus I squared. Well, every I squared, remember, becomes a negative 1. So now we have 2 minus I plus 1, which is going to be 3. 2 plus 1 is 3 minus I. So this one, you have to be careful with this multiplication. This one is going to end up being 3 minus I. Well, negative 4 plus 3 is negative 1, and I minus I is going to be 0. Then negative 1 times 1 is negative 1, and negative 1 times I is going to be plus I. So this is going also to add to be 0. So we're going to find that we found a factor using synthetic division of this complex polynomial. Okay, so my final answer would be negative 3x squared times 2 plus I x minus 1. Okay, that would be what I'd get after I did my division. So let's go through and just look at their slides. It's taking a while to exit the drawing. Okay, here we go. So our next one, again, is what we got. Then 3 minus I, which gives you the negative 1, and then that factors as 0. So you have to remember that when you're multiplying a complex answer by the complex divisor, you're going to have to FOIL that and be very careful and with your signs and changing that I squared back to a constant. Okay, and that's the same answer we got for the quotient. So we want the next thing, the last piece of this PowerPoint, is to construct a polynomial that has the given properties. It's a third degree polynomial, goes from negative infinity to positive infinity, and goes to negative infinity as x approaches infinity. So that means as x gets bigger, it goes down. So that means it's got a negative coefficient in front, and it has zeros of negative 3, 2, and 5. Then the b is a fourth degree polynomial, and we're given the 4 zeros, and it has a y-intercept at 0, 15. So let's look at a first. We need to change those zeros to factors. So the negative 3 becomes an x plus 3 as a factor. The 2 becomes an x minus 2 as a factor. And the 5 is an x minus 5 as a factor. So the 3 linear factors will give us, with 3 x's, give us a third degree polynomial. We know that's it. There's no complex factors. There's only these real number factors. So putting these together, we have p of x is equal to x plus 3 times x minus 2 times x minus 5. But here's the key. That's a positive x squared, which means that if we think of our end behavior that we learned earlier, it would go down on the left and up on the right. So we wanted it, the condition was it had to go up on the left and down on the right. So we're going to have to put a negative in front. So it's just going to be negative x plus 3 times x minus 2 times x minus 5. You could multiply all those out if you need to, but that is a polynomial written in factored form as it is. If you multiply them all out, then this is what you would get. Now, let me just talk to you about the process, possibly, of what might be the easiest way to multiply those out. I would take two of them first and multiply. Say we'll multiply x minus 2 times x minus 5. Okay? And that's going to give you x squared minus 2x minus 5x and plus 10. Or x squared minus 7x plus 10. Okay? Then you want to multiply that by, let me move that over a little bit. Okay, then we're going to take that and multiply it by our x plus 3. So we'll have x squared minus 7x plus 10. So with x plus 3, I have to take the x and multiply it by everything across. So that'll be x squared, x cubed, excuse me, minus 7x squared plus 10x. Okay? Then I'm going to have plus 3x squared. I'm taking the 3 and multiplying it by everything. Or you can do this. You can write it underneath. Sometimes that's easier. Plus 3x squared. Okay, minus 21x. 7 times 3 is 21. And then plus 30. Okay? So then when we have getting all three of these, I'll have x cubed minus 4x squared minus 11x and plus 30. But that doesn't account for the negative. So I've got to make everything in there negative. And so when I distribute the negative, I get it changes the sign of everything, and I get that. So just step by step, multiply two of them out, then add the third one. Then if there's a negative in front, change the sign. Okay, the last one. Again, we have a product of linear factors. They gave me the zeros. I changed the sign when I put it into the factor. Then the requirement is that the y-intercept has to be 15. So we have a problem. If we substitute the 0 in, y-intercept means my x is 0. Then I have 5 times 2 times negative 1 times negative 3. We get 30. So the y-intercept, if I multiply everything as it is not 15. It's 30. So to fix this, we can subtract. We can do a couple things. Might try subtracting 15 from the polynomial. What I usually do, we'll see what they do, and then I'll tell you what I usually do. P of x equals x to the fifth plus x plus 2 times x plus 1 times x plus 3 minus 15. But then it causes those to no longer be zeros, our original zeros. So we multiply by 1/2. But the way, and then you'll get that, and you can see that that's what it is. But the way to really, I think the easiest way to figure this out is to go back and let's talk about, there's an A, you can put you want to figure out what that multiplier is. And so what you want to do is you want to write your equation. You want to write it y equals A, okay, times x plus 5 times x plus 2 times x minus 1, because you don't feel like you just pull that 1/2 out of the hat, times x minus 3. Again, we change the signs as we put those factors in there. Now, we've got a point. We've got a point. They said the y-intercept was 15, so we've got this point, 0, 15, excuse me, that is in this. That's one of our points. And so this is our x and this is our y, and we've got to figure out what our a is. So we go back into our equation and say this is 15, okay? And we have a, and we're going to put a 0 in for all the x's. Okay? So we have a times 5 times 2 times -1 times -3, which is 30a. So 15 equals 30a. So a equals 15 over 30, which is 1/2. And so then you know that your fact, all you have to do then is go back and replace your a in your original equation. And that's going to be what you need to do. So in something like this, if they give you a point, just make it y equals. This originally was f of x, but I usually tend to put y. Make it f of x, a, and then all your list of factors, and put the values of x and y of that point and figure out what your a is, your multiplier, and then that's how you're going to do that kind of problem. Suppose that they had given you a point that wasn't an x-intercept or a y-intercept. Suppose they said something like f of 4 equals 7. Well, then you would have put the point 4, 7 in there, put 4 in for your x and 7 in for your y. Same process though, you would have solved it for a. Okay? So if it said it passes through the point 4, 7, I'll go back and work that one out too, just for the heck of doing it. If it passes through the point 4, 7, what you would have done, you would have said, you would have had your factors set up just like you did. Okay. And you would have then, you would have had your y and your a. And so 4, 7 is my xy, so 7 equals a times 4 of this plus 5 times 4 plus 2 times 4 minus 1 times 4 minus 3. So 7 equals a times 9 times 6 times 3 times 1. So that's 54 times 3, which I don't have a calculator in front of me. It's 12, it's 162, 162a. And so 7 over 162 would be a. It's not a pretty number, and it might reduce. I don't know if it reduces or not. But that would be what you'd put in for your a in your original problem. You won't have any with crazy fractions like this, but that's the process, if you want to know what the process is. Okay, good luck with 5-2.